In the last video, we left off at this example. It was an ethyl group on a nitro, an NO2 group. And we said, listen, folks, I know that I went on and on about benzene, and it was just one example of a delocalized network. But anytime we have these hybrid forms, these hybrid resonance forms can turn into a resonance hybrid, a true hybrid, which represents all of the forms that we can draw on a sheet of paper. And that's down here toward the bottom. All right, so I've been holding out on you, right? I've not yet told you how to determine if electrons, just based on structure alone, can actually be delocalized or not. So there's a few tricks, and we need to talk about these tricks because, folks, that's going to be part of the Blackboard assignments. That's going to be part of the upcoming test. Can you go through and determine which electrons are actually delocalized or not? So what are the rules? What are the guidelines? What things do I have to know in order to make this decision? All right, so number one, you need to keep in mind, folks, only electrons can move. If I start seeing things moving atoms and completely rearranging the structures, this is not really called delocalization. This is called something else, and sometimes it's called just a reaction. So we really only focus on the electrons. That's it. The electrons move, the atoms do not. Now the question, which electrons actually move? Well, the pi electrons are always the first go-tos. The pi electrons would be things like the electrons involved in a double bond. That would be pi electron. Well, a triple bond also constitutes a pi bond, right? They have two of them. That's why there's a total of a triple, a sigma and two pi's that begin to overlap. So pi electrons are a go-to questionable point that we look at as far as chemical structure goes and delocalization goes. Next are going to be the lone pair of electrons. So whenever I see a group of two that are maybe drawn on an oxygen or drawn on a nitrogen or another different type of atom that can hold these two electrons or this set of electrons or two electrons, then these are questionable ones as well. These are something that I want to look at as far as the molecule is concerned and say, are these delocalized or are these localized? So here's the question that almost everyone has. You told me that pi electrons and lone pair electrons are delocalized. No, I did not. No, I did not. What I'm telling you is that these are the start of a question. Are they delocalized? That's up for us to determine. And these are always the areas that we start. Double bond, triple bonds, areas with pi electrons, and then lone pair of electrons as well. Now, once I single these out, I have to make the decision. Are they or aren't they? And this is how we determine this. How do we know which one's which? How do we know which one's localized and delocalized? Well, here we go. Here are the rules for what I call electron pushing. Okay. Electron pushing is this concept that electrons can move. And sometimes we have to show that on a sheet of paper. We have to show someone, listen, this is how I'm going to draw the structure, but I need you to know that electrons can move throughout the molecule. So here are the rules. I'm going to write them verbatim, and then we're going to go back and do examples just looking at each individual rule. Okay? Number one. Pi electrons can move toward a positive charge. All right, so there's rule number one. If there is a positive charge nearby, then pi electrons can move toward it. They're more attracted to that positive charge. So of course they can move toward it, right? So this is delocalized network, delocalized electrons within a molecule. Number 2, pi electrons can actually move toward another pi electron set or a pi bond. We'll see why a little bit later on. Number 3, lone pair. Okay? Lone pair electrons can also move toward a pi electron set or a pi bond. And number 4, a single electron. We can't forget about the singles. They just don't go couples. A single electron can also move toward a pi electron set or a pi bond. So basically, what we've seen so far in organic, let's keep it in context here. We've talked about pi electron, folks. We've talked about pi's electron all the time, over and over and over. And we did that in the world of double or triple bonds. Well, they're not going to want me to introduce delocalization right now on molecules that you have no clue what they are. So basically, rule 1, 2, 3, 4 is telling me double bond moves toward a positive, a double bond moves toward another double, a lone pair of electrons can move toward a double bond, and a single electron can move toward a double bond. And if double bond doesn't suit your fancy, then triple bonds are okay as well. Those are the rules for delocalization. Now, I know that this might seem like a foreign language, so we need to go through and we need to do some examples. That way you can see how we represent delocalization on a sheet of paper and how you can make that determination or not. So let's start with an example. CH3, CH, double bond, CH, CH, CH3. And folks, this carbon is a carbocation. Oh, I see what he's doing. We have maybe a molecule that had a double bond. That double bond was broken. That double bond opened up 2 sites of attachment. Maybe hydrogen went on one of the carbons, and this is a carbocation that has formed. That's how this carbon has a full-blown positive charge on it. It's a carbocation. Folks, look at this. All the other lecture modules, we just trucked on, didn't we? And that's because we picked molecules that delocalization could not happen with. That's why we did that. At any point in time, if delocalization can take place, it affects our products. All of this is related to reaction theory. Every bit of it. So look at this. Rules of delocalized electrons. Rule 1, it said pi electrons can move toward a positive charge. Well, this means on a neighboring carbon. All right, so here's pi electrons, ding, ding, right there. And on the neighboring carbon, right, so this carbon's sp2. This is the carbon that has the pi bond right here. That's the one that's involved in the double bond. So the neighbor to it, the neighbor has a positive charge. Look at that. If this happens, this negative is right beside of a positive. They're neighbors. You know, imagine someone single living in a home, maybe an apartment, and then next door over, there's another attractive person that's also single living in the same apartment, and they get to know each other. I mean, they're side by side. They pass each other every day. And if they're attracted to each other, what do you think is going to happen? Folks, we get some movement. And some movement is happening in this molecule. And these pi bonds, these pi electrons actually go next door. Knock, knock. Are you there? Are you home? Would you like to have some company? And we see some electrons that move to the neighbor carbon. This is how we represent delocalized electrons. We are showing that these electrons can move. Well, if we do that, then this molecule is going to change, right? So this molecule is going to change, and this is how it changes. So I'm going to draw the original, just like I would in a reaction. I mean, that's really what all of this is going to boil down to. And here was a positive charge. So this was my original. This is where I started. So what we're saying is that the pi bonds can move from the double bond. Well, if it does, no longer is the pi bond there. And those electrons can move onto that carbon. Well, you know, truth of the matter be told, this is the sp2 carbon. So what it does is it just swings them around. That's all it does. So a double bond would form on the other side of that sp2 carbon. So that carbon's still sp2. And if it does that, this carbon that did have a positive charge, now's okay. It's got 4 bonds in total. 2 from the double bond on the left, 1 from the hydrogen, and 1 to the methyl group. So 4 bonds have been satisfied. The positive charge has now went away. But next door, folks, we got an empty apartment. Electrons have left there. Electrons have not went back at that point. And we see a shift in the carbocation. Do you see how this is going to start affecting reactions now? Delocalization is a pain. It is like carbocation shifts, right? Every time we had to watch out for carbocation shifts. 1,2 hydride shifts, 1,2 methyl shifts. And folks, now we've got to worry about, does delocalization happen? Because if it can, we get more shifts that end up with more products that we would not really expect in the very beginning. But here's the take-home message. Once this number 2 forms, right? So here's the number 1 structure and the number 2 structure. What do you think is going to happen? Folks, the rules of delocalization doesn't change. We have a pi bond on the right-hand side, and the neighbor next door is a positive charge. And we get movement again. So these electrons can actually be attracted to the neighbor once more. That forms the double bond to the left of that sp2 carbon, and the carbocation flops back to the original position. And that is why I did an arrow with double heads. This flip-flops back and forth, back and forth, back and forth, back and forth. It does it over and over and over. So with that concept comes the idea that these electrons move. They're moving through the molecule. They're not moving through the entire molecule, but they're moving through a part of it. And that's all that matters. And those electrons are moving throughout this area of the molecule. These 3 carbons are the ones that are involved in all of this, right? We have this center sp2 carbon, and that never really gets upset. It starts off on the left, and then it just flops them over to the right-hand side. That's where the double bond will end up going. And then it flops them back over to the left-hand side, and that's where the double bond ended up starting at, right? And the positive charge flip-flops back and forth, back and forth, back and forth, back and forth. We get this whole movement of electrons throughout that center area of the molecule. But that's the definition of delocalization. That's how we represent that with curvy arrows. This is a resonance form. This is a resonance form. Folks, I've got an option. I've got an option on how I want to draw these delocalized electrons throughout this molecule, right? So CH3, CH double bond, CH, CH, CH3. This is how we started right here, okay? If I wanted to show a resonance hybrid, which is really truer to the form that this molecule is in, how do I do that? Well, you gotta get rid of this positive charge, because the hybrid form doesn't really have a positive that has localized on one atom. That positive charge is getting flip-flopped back and forth. Where is that positive charge getting flip-flopped from? Well, sometimes it's on this carbon to the left, so I can put squiggle positive, and sometimes it was here, squiggle, positive. So right now, I am showing you the carbons that could have a carbocation depending on which resonance form it decides to be in. That's what the squiggle positives mean. What about the double bond? Well, folks, we know that a double bond is not stuck there. We know that this double bond can flip-flop. It could be here to the left, but it could also be here to the right. And this is the way that I show you both ways that they could form. This is a truer representation of the molecule. Not a true-blown carbocation, not a true-blown double bond, but it has tendencies to be that way. And that is the representation of a resonance hybrid due to delocalization. So folks, the first part of learning delocalization is learning how to identify it and then learning how to represent it. And this is how we do it. So let's do another example using the same type of rule. All right, so let's do CH2 double bond, CH, and then CH2, CH, CH3 with a positive charge here. So the question that you might be given, will delocalization take place, yes or no? And then if so, show the resonance form and show the resonance hybrids. Okay, well, let's check our rules. The rules say pi bond moves toward positive charge. And you're going to look at this and you're going to go, oh, look, a double bond. This is a pi bond. And look, a positive charge. So pi bonds or pi electrons are getting attracted to that positive charge carbocation. So yes, delocalization does occur. And if you write that on a sheet of paper, I'm going to go, and I'm going to give it back. That's wrong. Delocalization doesn't take place here. So the question is why? The ingredients are here. I know they are, but they're in different kitchens. It's not in the same one. Well, what does that mean? Okay, well, yes, you are correct. You do have pi bonds. Pi bonds are right there in that double bond. And you are correct when you say that this carbon has a carbocation. That is a positive charge. Yes, that's perfect. The ingredients are there. But notice what I did on the last example. I said that they have to be neighbors. So this is my sp2 carbon right here. That's the sp2 one. That means the neighbor carbon next to that one better have something on it in order for delocalization to take place. And it doesn't. There's no other sets of electrons here. There's not a positive charge that's here because we're talking about rule number 1. The positive charge is on the molecule, but the positive charge is further down the molecule. It's too far away. It's like a long-distance relationship. It's not going to work. And because of that, delocalization does not work with this molecule. It has to be on the neighboring carbon where those pi electrons are going to be located that you're so focused on. Rule 1, pi electrons move toward a positive charge. Well, you identified the pi electrons, folks. You've identified them, but it has to be on a neighboring carbon, and it is not. It is next to that neighbor, further down the molecule, and because of that, no electron shifts will happen, no delocalization happens, and folks, everything here so far, the way it's written, is a localized electron for that reason. All right? So that's how we interpret rule number 1. Okay, so let's do another example. Let's see if we are getting more comfortable with this idea. So let's do CH3, CH, and then maybe a double bond. CH, CH, and then maybe another double bond. and then a CH2. All right. Well, and you know what? Just to make it a little bit longer, let's erase that 2 and put a CH2 out here on the end. All right, so this whole thing is about positive charges, right? And here we have a positive charge on the end. That's where I'm going to put it. So this carbon has 2 hydrogens. It has a connector to the neighbor carbon, which is the 3rd bond. It's missing a 4th, so therefore that does hold a full-blown positive charge at this point. So this whole rule number 1 says, will pi electrons move toward a pi chart? And if so, then draw that form. So this is the questionable one. Do we have delocalized electrons or not? All right, so rule 1, pi electrons move toward positive. Well, here's a positive charge. Ding, ding. That means we've got that part of the definition. The next part of the definition means pi electrons. Do we have pi electrons? And you're going to go, yeah, I see some right here and I see some right there. So ding, 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 ding. We have those as well. Now, the question is, will they move? Just because they're there doesn't mean they're delocalized. If they move, they are delocalized. So will they move? Will the pi electron move toward a positive charge? Well, it's probably this set of electrons that we're going to be focused on because that's the closest to that positive charge that we know at this point. And the question now is it on the neighbor? So this is a sp2 carbon. So on the neighbor next door, is there a positive charge there? And you're going to look at this and you're going to go, yeah, it's right there. I see it. Right there to the right-hand side, I see a positive charge. So therefore, pi electrons can move toward a positive charge. And we can show that by starting an arrow here and pointing it to that positive charge, and now we have electron movement. So delocalization is going to take place here, and if it does, then we can rewrite that part of the molecule, right? So this double bond way down here, it's not really affected at this point, right? That's too far away from that positive charge. So we're not even worried about that double bond right now. Okay, so CH and then CH, there was a double bond right there. I'm just going to rewrite it. And then my CH and CH2. So this is what we started with. And folks, we said delocalization can happen. So we know that these electrons can move and that double bond can flip-flop to that side of the molecule. When that happens, this positive charge will also flip-flop and it will trade places. So this carbon becomes positively charged, right? That double bond was right here to the left, and it's that carbon that is now shortchanged. So we've just showed an electron movement. We've just showed delocalization taking part in that part of the molecule, but you got to be careful. It's not the only way, because look now at what has happened. We have shifted electrons. Delocalization took place. It shifted the carbocation from the end more toward the center. And guys, that's right beside of another double bond. Oh no. So now we've got another option. So we see the CH3 and we see the CH double bond, CH, which is where that new carbocation is at this point. And now we have this ending piece. And look, we have a pi set of electrons, an sp2 carbon right there, because it's got a double bond. And right beside of that is the new space for the carbocation. So these now can take place in delocalization. And if that goes on, we get yet another resonance form. And if that resonance form happens, what do we see? Well, up here at the top, I'm going to do the electron movement at that step because it can happen again. There we go. And then this double bond can flip-flop to the other side, so it can go here. That means that this carbocation is no more, and it flip-flops to the carbon that lost the double bond. There you go. There's the other resonance form for this particular molecule. Right there it is. So we actually have 3. This molecule has 3 resonance forms. This is form number 1 up here at the top, and then it shifts, forming the carbocation more on the inside. And folks, it shifts again, a third time, a second time maybe, and it goes to this carbon that's here toward the left. Well, 3 different forms, and they will all flip-flop back and forth, back and forth, back and forth between all 3 versions. So what that means is that I have to do a resonance hybrid. I want one structure, maybe, that shows where all of this movement can take place. I mean, that's really what I want to do. That's the purpose of the resonance hybrid. So this is how I do it. All right, this is where we started, right here. Okay. Now let's take a look at where the carbocation has landed. The carbocation started here at the very end in our very first example, didn't it? Well, we know that this carbocation is going to shift through the molecule. So what that means is that it's not really a full-blown positive. It is a squiggly positive. Okay, it is partially positive, because if it's not at that position, it can be shifted inward. And from the end, on the 3rd carbon from the right-hand side, 1, 2, 3, right here, we see that the carbocation could land at that position as well. So not a full-blown positive, it's a squiggly positive, because it's only there part of the time. And then it can actually shift again from the second one from the end on the left, right? We saw that that is where it could also land. So with this particular carbon, we actually see another squiggly positive, because sometimes it could land there as well, but it doesn't stay put. It's only there part of the time. So I can put these squiggly positives on all of these carbons to represent that this is where that carbocation could land. Now at the same time, I need to fix my double bond, because I know that this double bond doesn't stay put, right? It could be there, but it's only there part of the time. So I can put a dashed bond there. If I look at my second example, look at where that double bond has ended up. Well, it stayed true on the second carbon end, but this end double bond has moved toward the right-hand side. So this could have my double bond. That's true. That's great. But it's only there part of the time. Because that carbon that had the double bond could flip-flop it, and it could also put it here. Oh, look at there. There's a dotted line here. That's where a double bond could be. We see it right there. There's a double bond here, because that's what we see in our original example. There could also be a double bond at this position. So I got to do my dotted line there. Because look, folks, we drew it. It's right there. That's a possibility for it. And then here to the left-hand side, that's also where all of this started. So this original sp2 carbon took its double bond from the left and flip-flopped it over to the right, and back and forth, back and forth, back and forth, back and forth. Those are areas where that double bond could be. And then this original double bond, that sp2 carbon did the same thing. It took its double bond on the left and it flipped it over to the right. And it went right, left, right, left, right, left, right, left, like a march. And those are areas where that double bond could be formed. So down below is our example of our resonance hybrid right here. So the molecule really isn't this one, and it really isn't this one, and it really isn't that one. It's actually a hodgepodge of all three that we call a resonance hybrid. They're not true double bonds, they're not true single bonds. The carbocations are not staying put where they need to be. They are moving throughout the molecule. The electrons are not staying put where they need to be. They are moving throughout the molecule. You can imagine the mess that is going to happen as far as a reaction goes, because that means if I am trained on only looking for the carbocation and saying that is where my incoming group is going to go, that's great. But folks, you also have another choice because the carbocation moves. And then on top of that, you also have another choice because the carbocation moves again. How many different types of products are we going to get from this? This is the problem of delocalization. Right here, folks, you're looking at it. A lot of people are okay by the time I get done explaining the rules of being able to define if it's going to move or not. The problem is when it concerns reactions. How does it behave in the reaction scenario? That's where it's going to get you. All right, so we've got more examples. We've got more rules to talk about on top of this. So if you're okay, I'm okay. Go to the next video, hit the play button, and listen to me ramble again for probably another 20-30 minutes. I'll see you then.